Shall we begin? Let's. All right. So, yes, it's not today, it's Tuesday. Tuesday. We have the next assignment. All right, so we are talking about the simple harmonic oscillator, and as we discussed, it's one of the most important problems in physics, and so it's quite important that we focus on it in quite a bit of detail here. And so the first thing that we did last time, and I want to review and emphasize the important points, is just to look at the classical mechanics of the simple harmonic oscillator, written in this particular notation with particular emphasis on some of the particular features. So, first thing we did is that we wrote everything in terms of dimensionless variables. That's always what you should do. So you should always get rid of the units by looking at whatever the characteristic scales are in the problem. And whatever the problem is, it has some physical constants. In this case, there's two constants, the mass and the spring constant, or the mass and the resonance frequency. And that's it. But, so everything is kind of defined in terms of that. And at least that relates, whatever characteristic units we have will be defined in terms of those physical constants. So there's some characteristic energy, there's a characteristic length scale, there's a characteristic momentum. And by this, we have, they're loosely related in this way. I mean, whether we put a factor of 2 in there or not, that doesn't matter. That's because, of course, everything would be rescaled in terms of that. And I keep oscillating, my simple harmonically oscillating as to decide whether I want to put that factor of 2 in there or not, because there's no good solution. Let's figure this stupid factor 2 somewhere. Anyway, with that, the Hamiltonian looks like this. It's symmetric, it's quadratic in position momentum. They're completely symmetric. And as I say, whether this factor 2 is absorbed here or put there, your choice, but we'll choose this. So, in dimensionless units then, the Hamilton's equations of motion for the space-phase variables have this kind of symmetric form. Okay? And each one of those, the canonical variables, the position momentum, satisfy the simple harmonic oscillator differential equation, whose solution I've written here in terms of initial conditions. The initial condition for the position and the momentum, or I can think about it as the initial amplitude and the initial phase of the oscillator. Okay. So one important point here that I want to emphasize is that any simple harmonic motion that's oscillating at a fixed frequency, omega, can always be thought of as some amount of cosine and some amount of sine. Always. And those are sometimes called the quadratures of the oscillation, because they are 90 degrees out of phase one another, so they're said to be in quadrature. So it's like electrical engineering, ham radio jargon, radio, whatever, but that's what we talk about. We still talk about the quadratures of the oscillator, okay? Or I could equivalently think about any harmonic motion always can be thought about as having some amplitude and some phase relative to some phase that we call zero. So either I talk about the quadratures, which in this case are the x and p, initial x and p variables, or I talk about the amplitude and phase. And of course, they're interrelated with one another, right? So the amplitude is the, Pythagorean theorem length of that vector. And the phase is the argument of this, the imaginary part of the ratio of P and X. That is to say, any harmonic motion can always be expressed compactly in terms of a complex amplitude. Okay? So the complex amplitude encodes the amplitude and phase and the quadratures. It's either I talk about it in terms of real and imaginary parts, or I talk about it in terms of polar representation of that phasor, right? So if I have a complex number, which is, here's my complex plane, it has a real and imaginary part. And those real and imaginary parts are the x and p variables. Or equivalently, that complex number has an amplitude and a phase. Okay? I want you to keep those things in mind, because that aspect of the simple harmonic oscillator, that classical aspect, has quantum analogies and quantum features. And they're often forgotten. We learn about raising and lowering operators, but we have no idea what that means relative to classical oscillators. They mean something. Okay? So what this says is that, written in terms of the complex amplitude, simple harmonic motion is just the rotation of this phasor on a circle. The amplitude is constant. If given some initial energy, that energy is conserved, and that energy is just given by whatever the characteristic energy of the system is, times the square of the amplitude. Okay? And the trajectory is thus a trajectory on a circle in these dimensionless units, in these scale units, that rotates at an angular velocity omega. Okay? That's what that means, is that the position of the particle, as I project on this, is oscillating back and forth. And the momentum of the particle is oscillating back and forth. And they're oscillating back and forth 90 degrees out of phase with one another, right? So when the position is at its maximum value, the kinetic energy is 0. When the position at its minimum value, the kinetic energy is its maximum value. You know that from basic simple harmonic motion. Okay? So that's the classical problem, and I want you to think about it. I want you to think about the complex amplitudes. I want you to think about what the real and imaginary parts mean, what the amplitude and phases mean. Okay? All right. So then what we did is we said, okay, now we're going to quantize this. And the way we just quantize it is to just say, now my position and momentum canonical coordinates become the position and momentum operators, which no longer commute. They have the canonical commutator, and now we have one more constant in the problem, h bar. Before we just had 2, mass and frequency. Now we have a third one, the characteristic unit of action. So it's natural to define the characteristic position momentum variables to be related to one another such that they are equal to the characteristic unit of action in quantum mechanics, h bar. And now we got 3 constants and 3 characteristic units, and so we can define them. We get the natural characteristic energy scale of the harmonic oscillator, h bar omega, and these are the characteristic scales of position and momentum. Okay? And so expressed in terms of those characteristic units, we now have a dimensionless position and momentum operator. And moreover, we have a quantum analog of of the complex amplitude. So what was the complex amplitude, a complex number in the classical mechanics, now is a non-Hermitian operator in the quantum world, whose Hermitian part is the position and whose anti-Hermitian part is the momentum. Okay? And you will keep that in mind. What is different, of course, in quantum mechanics is that whereas alpha and alpha star were numbers, now A and A dagger are operators and they don't commute. Okay? And their commutator is the canonical commutator. It's another way of writing this commutator. Okay, so expressed in terms of those dimensionless variables, our Hamiltonian, here's our characteristic energy scale, x and p, or in terms of the complex amplitudes, looks like this. Okay, the point is that because A and A dagger don't commute, we have a symmetrized form of what was here. All right? Okie dokie. So there's a new operator that appears, the amplitude squared, the square of the complex amplitude, classically is the thing we call the number operator, quantumly. I think quantumly should be an adverb. That thing, the number operator, for reasons that we know that its eigenvalues are the numbers, the natural numbers, has these commutation relations with A and A dagger. And we use them to solve the time-independent Schrodinger equation, that is to say, to solve for the energy eigenvalues of the Hamiltonian. Okay? Because the energy eigenvalues are the eigenvalues of the number operator multiplied by h bar omega plus a half, right? And what we showed in lightning speed at the end of last lecture is that that number operator, its eigenvalues are the natural numbers, the non-negative integers. 0, 1, 2, 3, all the way up to infinity. Okay? And so the energy eigenvalues of the simple harmonic oscillator are h bar omega times n plus a half. So the energy eigenvalues are, yes?
Are there any other potentials that have the same spacing, the same like?
No. Absolutely. That's a good question, and the answer is no. So this, as he was noting, of course, what is unique about, or what you see about the harmonic oscillator, and in fact is unique to it, is that the energy levels are equally spaced. They're all spaced from one another, h bar omega, and that is unique to the simple harmonic oscillator. That is a feature of the simple harmonic oscillator. So if you have that, you have a harmonic potential. Of course, the lowest energy state is the ground state, and the ground state is the state with n equals 0, and it has an energy that's a half h bar omega above the bottom potential. That's called the 0 point energy. Okay. And moreover, we showed the algebraic properties of the A and A dagger, which we call the raising and lowering operators, or lowering and raising operators. That is to say, those operators take one of the number eigenstates and either lowers it by 1 or raises it by 1. Okay? And of course, there is a ground state. That's how we derive this fact. And that ground state has the property that it is annihilated by this. This is why sometimes this is also called another name, and it becomes more important in the context of field theory when these n's are quanta of excitation of the field are particles. Then this is known as the annihilation operator. And A is the creation, A dagger is the creation operator. And with this, these two properties, what it says is that I can obtain any of the energy eigenstates, the number states, by applying the creation operator or the raising operator, they're the same thing, n times to the lowest energy level, the ground state. And then we have to renormalize it because this is not a unitary, it doesn't preserve the norm of this, and you renormalize it. And that norm is n factorial. It's easy to check. Okay? So just come back to the front board here for a moment. What it's saying is that quantifully, whereas classically, sort of any, remember we said the radius of this circle represented the energy of the system. And the system starts there and just rotates that. The quantum state says, in some sense, there's quantized possible trajectories in phase space, all separated by h-bar omega. Now, of course, that's not exactly true because I don't know, it's supposed to be a circle, but you get the picture, I hope. Because, of course, I can't be at a point in phase space. I mean, there's a kind of uncertainty level here, and there's some kind of, and we're going to talk about this in much more detail, how to think about this. There's some kind of uncertainty here in terms of x and p in these guys, okay? But loosely, that's a good picture of what's going on. And the reason you could think about the existence of the zero-point energy is, as we discussed when we thought about the particle in the box, is from the uncertainty principle. It's impossible to localize at position and momentum simultaneously. The ground state would be just there. That would have that position and no kinetic energy. That's impossible. But the ground state is the minimum energy state that consistent with the uncertainty principle. All right. So far, so good? Very good. All right. Now, one thing we can see from here, firstly, is that what we call the number states, which are the eigenstates of the number operator, which are also the energy eigenstates. Of course, here n equals 0, 1, 2, infinity, form a basis for Hilbert space. We know that the eigenvectors of any Hermitian operator form an orthonormal basis, right? And so, and of course, in the context of the simple harmonic oscillator, unlike, say, the finite square wheel, all the states are bound. There are no unbound states. So this is the complete basis. So a resolution of the identity can be written in terms of the number states. And that is to say, a basis for Hilbert space. And what is Hilbert space in this case? It's the space of square normalizable functions on the real line. That's the Hilbert space we've been talking about for one-dimensional mechanics of a single particle. So this forms a basis for Hilbert space, which means that any observable, or any operator, I should say, can be expressed in this basis. So for example, we can write the position operator in this basis. We've written position and momentum in terms of continuous variables, the x eigenstates and p eigenstates, but we can, and we often do, write them in terms of discrete variables, the number states. So even if I'm not talking about the simple harmonic oscillator, this is a basis, right? It doesn't matter whether they happen to be the eigenstates of the Hamiltonian. It's always a basis. Yes, Stephen, you have a question.
Yeah, I know physically the annihilation and raising operators cannot hit anything below n equals 0, or yes. But my question is, it does seem like anything will change if you make n negative, apart from the fact that you get imaginary terms.
The reason that those states don't exist is the following. N itself is a positive operator, meaning that its eigenvalues have to be positive. And we saw that last time. That's because if I look at the expectation value of n with respect to any state, that is equal to that. And that is equal to the norm squared of this vector, which is always greater than or equal to 0.
Yes, but if you make n like -2.
But then n would have a negative eigenvalue, and it can't. Okay, so that's how we got to that. All right. Very good. So because this is the basis, let's write the matrix representation of x and p. We can do that. So what are x and p? How do you do that? Well, whenever you're dealing with the number basis, the thing to do is to express things in terms of A and A dagger. Okay, because we know how A and A dagger act on this. So what is x in terms of A and A dagger? I ask you.
A plus A dagger over root 2.
Thank you very much. So it's the real part with the factor of root 2 in there that annoys us. Okay? And P is what? The imaginary part. So that's A minus A dagger over 2I, and then there's a factor of root 2 there. Okay. So if we know that, then we can express x and p in terms of this basis, because we can always write A and A dagger in that basis. Let's do that first. Okay? So let's look at, for example, the annihilation operator in the number basis. Okay? So I'm just going to insert a resolution of the identity on both sides. I'm just going to do it that way. So I'm going to have a sum over n and n prime. Okay. And so this is equal to the square root of n minus 1 delta n prime n minus 1. Okay. So this then is equal to the square root of n, but because I can't have n less than 0, this goes from n equals 1 to infinity, n minus 1, n. Okay. The case where n equals 0 doesn't exist because that term is 0. So that's important. Square root of n, sorry. And A dagger is the adjoint. That's just taking the adjoint. Or if I want to just relabel things and start at 0, I can do that too. That's just relabeling the sum. So, how do these, this is just expressed as a set of outer products. I mean, you see what this thing does. It lowers it. It takes n to n minus 1 with that coefficient. Or I take n to n plus 1 with that coefficient. Okay, let's write them as matrices. Of course, these are infinite dimensional matrices, right? So we can't write down the whole matrix, but we'll write down a few of the matrix elements of it. So our basis elements, 0, 1, 2, dot, 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 etc. Of course, it has nothing on the diagonals. Right, this is row column 1, and column 0, column 1, column 2, dot, dot, dot. And then it has something on the off diagonals. And you tell me, is it on the upper diagonal or the lower diagonal? Lower. Because if we see here, this is row column, right? So it's 1 through 2 through 3, dot, 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 0 through n. 0 is everywhere else.
And for a dagger to be the opposite side.
Exactly. So a dagger looks like okay. And so X is this plus that over 2, root 2. And P is this minus that over that. So it'll have things on the upper diagonal and the lower diagonal, etc. So we can write X and P as matrices. These, unlike the position and momentum eigenstates, the number states are valid states of the Hilbert space. Okay? That's why we get a representation of X and P as matrices. They should be. Because this Hilbert space, it has a countably infinite basis. Here's an example of such a basis. All right, good.
That's where,
Please.
Okay, so you're saying that in this basis, the X is just better behaved? I'm just trying to figure out,
Yeah, all I'm saying is that it has the behavior that you would expect from any operator on a Hilbert space. It's a matrix. The fact that we expressed it, I mean, let's talk about the position of momentum bases for a moment. Okay, so let's talk about, so now these are the eigenstates of the number operator. They're also the eigenstates of the Hamiltonian. Now we can look for the position of momentum representation. Okay. So the way we said that we looked for states that are eigenstates of the X operator and the P operator. Now these are continuous variables. but that's okay. They allow us to write a resolution of the identity. Okay, so that's okay. And let's see, do we have any more chalk? Now, you know, so whereas these operators expressed in this basis have matrix elements that are just numbers, in this case, the matrix elements of X and P have singularities in them, right? This is X times a delta function, which moves up. So it's in some sense not very well behaved, right? And P in the representation of P eigenstates also is a grand function. And the momentum operator in position representation was the derivative of the gradient or the derivative operator. And the momentum operator, the position operator in momentum representation is the derivative with respect to. Notice the H bar went away because this is dimensionless units. Okay. Yeah.
This looks exactly like what we did before, but in the character scale.
That's correct. That's exactly what it is. Indeed, let's just to emphasize that, let me say one quick point. Recall that with the units in the problem, the kets X and P had units, right? So recall, with units, we had these guys. So these are my little variables have the units, right? Which meant that this thing has units of 1 over the square root of length, and P, ket, has units of 1 over the square root of momentum, which is the square root of H bar L. Okay. So I can define the dimension full ket in terms of the dimension less ket as 1 over the square root of the characteristic unit, where x is equal to xc times x. Now this thing has units. Or said another way, the dimensionless ket is related to the dimension full ket by getting rid of the units. Then, when you do the change of variables, this will get you back that. So, you know, if I look at, for example, x prime in the dimension full variables, Well, they said that was h bar over I d by dx delta x minus x bar. But if I wanted to do all that re-expressing over here, this is going to be, you know, I don't want to go through it. You see it, there's going to be a root 1 over root 2, 1 over root x, that gives me an xc, put it over here, and then I get a p, 1 over pc, and I get my h bar. Okay. All right. Moreover, of course, what we have is that I can talk about position and momentum representations. Okay. I mean, let me just quickly go back over here before I said it. Of course, in the number basis, what that means is that I can write the state as an expansion over the number eigenstates, and the C sub n's are just the probability amplitudes in the n basis. With respect to the continuous variables, we have a similar thing, but I try to write every side as a superposition of position eigenvectors that way. Or momentum eigenvectors, where those are the position and momentum wave functions. So psi of x is that, which if I wanted to write it in dimension full form is that times that, for those are dimension left full variables. Gets rid of that. And the momentum space wave function in dimensionless variables is that. Finally, what about A and A dagger? Well, to do what I can see is the following. Let me first say the following thing. If I look at the momentum operator acting on the state and look at the wave function, we of course know what we get. We get the derivative with respect to x. That's the momentum operator is a derivative operator acting on the wave function, or in momentum space, the x operator acting on the state looks like a derivative with respect to p, to the other side. So what about the creation annihilation operators, or the raising and lowering operators? What do they look like in position and momentum space? Well, they're combinations of x and p, so let's just do it. So if I look at, suppose I take the annihilation operator and I act it, or the lowering operator and act it on the side. What is the wave function I get? Well, to do that, I look at the position representation. Okay, so that's equal to the position represent, A is x plus IP. Over down. So this is equal to x. I'll just write it all out. 1 over root 2 x hat psi plus I P on psi in the position representation. So far, so good. What is this? It's x times the wave function, right? And what is this? It's the derivative, right? The momentum operator in position space is the derivative.
All these x's are the new.
Yeah. Dimensionless. Everything's dimensionless. Sorry. Yes, pardon me. Let me be quite much more careful about my notation here. Sorry. Thank you. Plus I times the derivative with respect to x. Okay. So in the position representation, the annihilation operator acting on this is x plus the derivative with respect to x acting on the wave function. What about the moment? And of course, a dagger is just the adjoint of that. And the adjoint of the derivative is minus the derivative. All right. What about in momentum space? What do the position and the creation annihilation operators look like? Right? X plus IP in the momentum representation. And what do we get? What is this guy? It's got to be by dt. It's got some i's in there. You got to think about it. It's 1 over minus I d by dt. And then what is this guy? I times p. Thank you very much. Times the momentum space wave function. Okay. So in the momentum representation, this is I over root 2 p plus d by dt. So up to this overall phase of I, the annihilation operator and the position momentum representation look the same, which you kind of expect because they're kind of symmetric in x and p, except an overall fact, some i's floating around there. Okay. And of course, a dagger if you put the minus sign there. Very, very good. Alrighty. So, given that, how do we find the position or momentum representation of the energy eigenvectors? That is to say, the wave functions that are the energy levels associated with the energy levels of the simple harmonic oscillator.
Rewrite the Hamiltonian with these? Or?
We could. So one way we could do it is that we could express, so we seek the position or momentum representation of the energy eigenvectors, right? Now, one way we could get at them is to solve the differential equation, right? I agree with Keith, we went. But I agree. And so, sorry, I mean, what that would, one way is to say there's a differential equation. In the position representation, we know that this is, we got rid of the units there. H bar omega on the wave function is H bar omega n plus a half u. So this is the time, this is H psi equals E psi. And we could just try to solve that differential equation, which is the way it's always done, or used to be always done, in introductory quantum mechanics. You plug in a power series, and you'd see the power series eventually has to truncate because you can't satisfy the boundary conditions unless that, and that's one way to get at the eigenvalue equation that we got algebraically, just based on the theory of operators and positive operators and so forth. But another way is to use the one thing we know, which is that there is, for the ground state, we have a very simple equation. It says for the ground state, we're annihilated by the lowering operator. And we can express this equation as a differential equation. And just solve that. And once we have the ground state, we have all other states, because all other states are obtained by just raising that n times. So what we're going to do is do that. Much easier, and let's just do that. But I agree, this is, you can do it, and that's perfectly correct. Thank you. All right. So how are we going to solve this equation for the wave function? What we seek is the wave function u0, the ground state wave function.
N would be 0.
Yeah, so n would be 0. So we don't want to solve this equation, we want to solve that equation. So how are we going to use this equation to find u0?
Then it would 0 A dash.
If I did that, I'm going to get 0 equals 0.
Hit it with the next cat, so you have it in basis.
Say again?
Hit it with the next cat, so you
Yeah, I want to express this in the position representation. That's what I want to do. I want to look at this equation, because that's going to be a differential equation. And we have that over there somewhere. The annihilation operator in the position representation is equal to 1 over root 2 x plus the derivative with respect to x on the wave function, which is what we're calling u0. Alrighty, good enough. So, ground state wave function satisfies the following differential equation: x plus d by dx on the ground state wave function is 0. So that's a simple differential equation we can solve. I hope we can solve it. course, this is really in 1D without time dependence. This is an ODE, not a PDE. So how do you solve that differential equation?
Separate it.
Separate variables, thank you very much. Right, it says that the derivative with respect to x is equal to minus x naught, which says that the integral du naught or u naught to minus the integral dx x, which is minus a half x squared. And this is the natural log of u naught divided by some constant, call it a. So we have the solution. The ground state wave function is of this form. Let me just call this some constant c. You recognize that function?
Yes, that's like in homework.
What is it?
It's a Gaussian.
It's a Gaussian. That is a Gaussian. How do we find this constant c?
Normalize it.
Normalize it. Thank you very much. Excellent. All right, so the norm of the vector square we can do as an integral in position representation. So that's minus c squared. Which is what? That's equal to
Is that a root pi over 2?
square root of pi. Pi, I believe. I double check that. I know if it was over 2, it would be,
Yeah, that's right. So it's
yeah, I think that's right.
So it's not pi over 2?
I think it's this. We'll check.
You do like square root of pi over whatever in front of you.
Yeah,
Yeah.
that's right. It's square root of pi rating. That's right.
I had to remember that.
Yeah. I only know it when it's normal. And I,
It's probably
Just need to see.
Okay, it's good. All right, and we want this to be equal to 1 to normalize it. Right? So what do we choose C to be?
more pi over 4.
That's right. Now, of course, there's an overall phase that we can always put in front here, but by convention, we choose this to be 1. Doesn't matter, but by convention, we do that. Okay, so that says in dimensionless units, u naught is 1 over the 4th root of pi e to the minus a half x squared. In dimension full units, I have to put in a 1 over the square root of that. Okay. putting in what xc was, the characteristic unit. Remember, xc was the square root of h bar over m omega. This is equal to h bar over m omega times pi to the 1/4 power e to the minus a half m omega x squared over h bar. Yeah.
So, I mean, I guess classically thinking about a harmonic oscillator, I would expect it to be most likely to be found where its speed was approaching 0 at the ends and not in the middle where its speed is the highest.
Indeed, that is an excellent piece of observation. And that is something which is saying that this kind of motion is extremely non-classical. Now, I was going to save this for next lecture, but let's talk about this now. So, well, let me hint at something. So as Zeke was suggesting, let's think about a pendulum, right? A pendulum, it's a simple harmonic oscillator, spends a lot of time at the turning point and then speeding through the center. So you kind of expect the highest probability for it to be is at its turning points, and the smallest chance of finding the particle to be in the center. And this is the opposite. If I look at the wave function,
Is it because here, when it's at the tip of the swing, its position is very narrow, but so its momentum must become very large?
no, you cannot talk about, the problem is, you can't talk about the position and momentum simultaneously. Classically, so this wave function is supposed to be a bell shape, right? This is the square of the wave function. So classically, we could talk about the position at a particular, the momentum at a particular position. We could do that classically because we could talk about position and momentum simultaneously. And what is that? Given a certain amount of energy. Well, it's whatever the kinetic energy is at that point tells me the momentum. So that's the square root of 2n e minus d, right? So where the energy at the turning point, the momentum is 0, right? And you expect it to stay there a long time. Now, what we talked about, very briefly, but we did talk about this, is the WKB approximation. The WKB approximation is a way of writing down the wave function when the momentum is large compared to the characteristic scale of change of potential. So when the de Broglie wavelength was tiny compared to something having to do with the rate of change of the momentum. In this case, this is the spring constant. So for very, very short wavelengths, which in this case means high energy, we expect the following to be true. That this is equal to 1 over some constant, normalization constant, divided by the square root of the classical momentum, e to the I integral the classical momentum integrated. Remember this? So this is a semi-classical approximation. So we expect this to be true, which is to say that for large energies, where the de Broglie wavelength is very small. So here's my harmonic potential again. We have the ground state. The ground state wave function looks like that. We'll talk about the intermediate cases in a moment. But if I'm at large n, well then this should be an good approximation of the wave function, which means the wave function should have a lot of its probability amplitude where the classical momentum goes to 0, and very, very little of it. So, so up here, I mean, classically the probability goes to infinity, small over here, and very high. Again, this is the classical probability based on this amplitude. And what we get is something that looks like this. It's supposed to look symmetric, I'm sorry. So, in the limit of large quantum numbers, that's to say a high energy, we have the situation that you intuited and that you expected. The probability amplitude should be very high at the classical turning points and very small at the place where it's speeding by the fastest. The classical dynamics is informing in some way what the wave function is, okay? And we saw that in a few lectures back when we looked at how the amplitude, and phase of the wave function obeyed equations that were the classical Hamilton-Jacobi equation. Okay? So this is sometimes known as the correspondence principle. Now, we're going to talk about this a little bit more and try to understand that somehow at the limit as n gets large, or I should just say En, whatever the potential is, En is large. You get to the classical limit. Now what we mean by classical is a very slippery term. In the sense in which this state is supposed to be symmetric, you excuse my horrible drawing, is a classical state. Well, that we can think about the semantics of the word classical. But what is certainly true is that this is true. That's to say, the wave function is well approximated such that its magnitude is guided by the classical trajectory. But for for long wavelengths, for low quantum numbers, the wave nature of the motion dominates, not the ray trajectory, in which case it has nothing to do with the classical trajectory. Nothing. So excellent, excellent observation. All right, so we have the ground state. What about the higher excited states? Well, firstly, what can you tell me just from what we know about the nature of the potential and the solutions to wave mechanics at 1D about what you kind of expect the wave function to look like?
It's not a node, right?
Yeah, it's got another node. So you kind of expect it to look something like that, right? And then what about the next excited state? I mean, it's supposed to be right there.
Like 3 Gaussians in a row.
Kind of like, you know, something like this. And you know that this is symmetric and isometric. Symmetric and asymmetric. Blah, blah, blah. This is really symmetric. Okay? It could be antisymmetric one too. Why am I saying that the eigenfunctions of the Hamiltonian are necessarily symmetric and antisymmetric functions of x?
Potential is symmetric.
Because the spectral is symmetric. Potential is reflection symmetric, and thus we know that the eigenfunctions are eigenfunctions of parity. Okay. All right, very good. We're learning something. We didn't already know it. Okay, so algebraically, we have this. Okay? Which means that the nth energy eigenfunction is given by write it out here. And so this is the nth power of a dagger, which is over there, a dagger in the x representation. So this is 1 over the square root of n factorial. 1 over the square root of 2 to the power of n. X minus d by dx, n times acting on E0. Right? So we just have to do that. And it's a pain, but the answer is that this time, every time I take this and do this derivative, well, I'm going to get the Gaussian back, right? Because you take the derivative, you get the Gaussian, and then you're going to get some derivatives of the things in the exponents, which are going to be polynomials in x. And so this thing is equal to some polynomial, the nth polynomial, x times the Gaussian. And these polynomials have a name. They're called the Hermite. The Hermite polynomials. I have to double check the facts because the Hermite polynomials have a certain factor in front. Yeah, I forgot that stuff, the square root of pi thing. So this is equal to this. 1 over square root of 2, where am I doing? Right, times over 4 through pi. Because that was U0. Okay, so those are called the Hermite polynomials. And the Hermite polynomial, so by definition, I could write a Hermite polynomial as what I get when I take this derivative n times on the Gaussian and then get rid of the Gaussian part. Okay. So, here are some of the Hermite polynomials. H0 is 1. H1 is linear. H2 is quadratic, etc. Notice they alternate from even to odd functions. So H and due to the reflection symmetry, I either get plus or minus stack. And this is what they look like. You take those polynomials, you multiply them by Gaussians, and you get, these are the eigenfunctions of the simple harmonic oscillator. Now, I'll leave it as a simple exercise for you. To show the following. That in the momentum space representation, so I should, and then before I do that, let me just quickly say, so what we have here is that in the position representation, UN is equal to some normalization constant, A sub n, times a Hermite polynomial, e to the minus x squared over 2. Okay. And if I write out all the factors here, that in the dimension full version, if I had any thought whatsoever,
Just in a drawing.
putting back all the units here. UNX is equal to 1 over the square root of XC pi to the n in factorial the Hermite polynomial x over xc e to the minus x over 2 xc. Okay, what about in momentum space? Well, firstly, we can see right away what is this. Well, again, we start with the equation that we annihilate the ground state. And in momentum space, this is the annihilation operator times I over root 2. Right? And this, I can cancel. So what can you tell me about the momentum space wave function of the ground state? Look at that equation for position space.
Same dimension.
It's exactly the same in these characteristic units. So in the characteristic units, this guy is exactly the same. It's exactly the same Gaussian. It's also Gaussian in dimensionless units with exactly the same width. Therefore, what are the excited states?
Same.
They're exactly the same, except there's some factor of I by convention, right? So this thing is I to the n times, the whatever normalization constant I have, Hermite polynomial e to the minus p squared over 2. Up to that phase convention, they're exactly the same. And this, again, is unique to the simple harmonic oscillator. And the reason is that in the simple harmonic oscillator, x and p are the same, right? The simple harmonic oscillator, the Hamiltonian, was x squared plus p squared with some units. So whatever is true for x is also true for p. So the position wave functions look just like the momentum wave functions. They're the same. It's the symmetry in x and p that makes the simple harmonic oscillator special. All right, we shall continue this discussion next time.